Since power functions have a number of different shapes, they often are very similar to other types of graphs, particularly exponential and log graphs. So I want to look at the difference between the exponential functions and the the exponential and the power functions when we have this concave up shape and an increasing exponential graph. So take a minute to look at the two graphs. The red graph is the exponential function. The blue graph is a power function. I did simple ones, 2 to the x for the exponential and x squared for the power function. So if you're only looking at quadrant 1, so kind of ignore what's on the other side, because obviously on the other side there are differences. But just at quadrant 1, how can you tell the difference between the exponential and the power? So you might pause the video, think about that for a minute, and turn it back on. There is one major difference that I want to point out that is probably the biggest clue here, is the y-intercept. The power function goes through the point 0, 0. Because if I have f of x equals ax to the b and x equals 0, then y is going to equal 0. And that's, of course, for b greater than 0. In an exponential function, I have f of x equals ab to the x. So if x is 0, y is a times b to the 0, which is just a. So it's always going to go through the point 0a. And it's going to have a y-intercept. So exponential functions have a y-intercept that is not at 0. This goes through 0, 0. This never goes through 0, 0. Now it might be that unless you shifted it up or down with a transformation, but the original parent function doesn't go through 0, 0. So that's the big deal here, is exponential power. Now, in the long run, which graph increases at the faster rate? You can see at first the exponential graph starts higher than the power function because its y-intercept is higher, but then the power function passes it up, but then they're kind of running along together, and it looks like maybe they may cross again up here. So what happens in the long run? So let's look at what's happening with the x squared graph. Whatever x is, y is the square of that. So if we fill in the next one, this would be 16, 25, and 36. If you say 2 to the x, what's happening is these numbers are doubling every time, times 2. 1 times 2, 2 times 2 is 4, times 2 is 8, times 2 is 16. So they do hit the same value again right here. So they're hitting the same value at 2, and they're hitting the same value at 4. But then after that, when we continue to double, 32, 64, if we went up to 7, this would be 49. This would now be 128. So in the long run, any increasing exponential function will grow faster than any power function. So in the long run, any increasing exponential function will grow faster than any power function. You often hear this in kind of casual terms in just when some people are talking about how fast something's growing, say it's growing exponentially. That's because exponential growth does grow very quickly. Now there's also there's a lot of similarity between the shape of a decreasing power and a decreasing exponential graph. They both have this downward curve. They both have the same asymptote here for both. But there's a difference in that the power function does not cross the y-axis, but the exponential function does. So here's the big difference here. Power, exponential. So if we have y equals ax to the b, and b is less than 0, then we're saying that we can't divide by 0, okay? So this is the same as 3 over x to the positive 2.1. We can't divide by 0. So there is no y-intercept. Because x can't equal 0. On the exponential graph, though, if we have y equals a b to the x, and we say x equals 0, we saw earlier, then y is just going to equal a. So it is always going to have a y-intercept at the point 0, a. Okay, so this does have a y-intercept. The exponential function does cross the x-axis or the y-axis. The power function does not. It has an asymptote here. Now this is going to come in handy when we're looking at modeling real-world data with this. Is it reasonable that the graph should have a value when x is 0, or is it reasonable that it should not? So we'll have to think about that. The last one we're going to look at is the concave down shape of the increasing power function versus the logarithmic graph. So once again, I want you to notice what's happening with the x-axis here. So with the power function, we see that the graph, once again, starts at 0, 0. So we have this point at 0, 0, and it curves down here. But the log graph, I don't know if I said exponential before, I meant log. The log graph does not touch the y-axis at all. It goes through this point right here. So and this is an asymptote. This has no y-intercept. Okay, so that's the main difference between the log and the power function. Now, both of them are growing very gradually. You can see they do both continue to go up. There's never a place where they totally flatten off and quit growing. So for the log function, even though it's very flat, we do have from negative infinity to infinity for its range. For the power, it's just going to be from 0 to infinity for its range. But in the long run, which one is going to grow faster? In this case, it's the power. The power function will always grow faster. Log graphs, I'll say, flatten out more, although they always keep growing. But always keep growing. They just grow at a very, very slow rate. So if we think of, for example, log base 2 of 2 is 1. Log base 2 of 4 is 2. Log base 2 of 8 is 3. Log base 2 of 16 is 4. So notice the x value is growing at a much faster rate than the y value. That's why it's growing so slowly in the y direction.